Okay, from this chapter, we will be studying some specific important stochastic processes in turn. And in this chapter, we will introduce the Poisson process. Okay, so this is not Poisson, it's Poisson. It's a French name. Actually, it means fish in French, but it's a person's name, mathematician's name, who supposedly proposed this process for the first time. And let's just move on to the definition first. And now we consider a random variable that depends on time. So this is a random variable that takes integer values, including 0. So this can take values of 0, 1, 2, 3, and so on. And this t, the parameter t, can take any non-negative real values. So, okay, t is a real number from 0 to infinity. Okay, so this is a random variable that depends on time. So here's the probability distribution of this random variable. We call it Pn of t, which is the probability that this random variable takes the value of some integer, non-negative integer value n, and that is given by this function, lambda t to the power of n exponential of negative lambda t over n factorial. Okay, and as I have stated already, t is non-negative real number, and this lambda is a positive real number. Okay, it's a parameter of this distribution. It's a given parameter. Okay, and this n takes the value of 0, 1, 2, and so on. So, of course, 0 factorial is 1. This is the convention we adopt usually. And also, when t is 0 and n is 0, we will have 0 to the power of 0. So this value is assumed to be 1. Okay, so this is a convention we adopt. Okay. So the random process, that is this random variable, time-dependent random variable, is said to be the Poisson process if the distribution of this random variable is given by this function. Why is it called a Poisson distribution, Poisson process? Because this is a Poisson distribution, right? This is a Poisson distribution with parameter lambda t. Okay, so if we fix t, and lambda is a constant, so lambda t is fixed, then this is the parameter of this Poisson distribution. Okay, so it's a Poisson distribution with parameter lambda t. So this is the distribution of this non-negative integers. Non-negative integers. Okay. So if you look at this this definition, you should notice that there are two things that can move. That is n and t. So these are two ways of looking at this distribution. So first, if we fix n, then t can be considered as a variable. So Pn of t. So we can plot different functions depending on the values of n. For example, if n is 0, then p0 of t is given as, so this one, this part should be 0. So that is just exponential of negative lambda t. So when n is 0, this is the function. So that should look like something like this. So it's exponential function. Since lambda is positive, it's a decreasing function. So it converges to 0. So that's p0 of t. And if n is 1, then we have, so lambda t times exponential of negative lambda t. So, well, I don't know exactly how this behave, but when t is 0, this probability should be 0, right? Because this t is 0. So it takes this value. When t is very large, then this converges to 0 because it converges to 0. This exponential part converges to 0 faster than this linear part diverges to infinity, right? So when t is large, it is very close to 0, somewhere here. In between, when t is small, then this increases. So this is nearly, so this t is close to 0, so this is almost close to 1. But this increases linearly with t, so it will increase something like this. At some point, it starts decreasing. So p1 of t should look something like this. And you can plot a similar thing for n equal to 2 and 3 and so on. So that's one way to view this function. And another way is to take n as the variable and fix t. So when t is 0, then everything is, so this part is 0 and this part is just 1. And according to our convention, 0 to the power of 0 is 1. So when n is 0, when t is 0, then it should be, it should have the value of 1. And everything else is 0. Right? So n1 and equal to 2, 3, and so on. So everything else should be 0. And it's a discrete distribution, right? Because n is an integer variable. So this is 1 and everything else is 0. And when t is some positive number, then it should have some value. Okay. Well, if t is sufficiently large, this is a Poisson distribution, so it can be approximated by a Gaussian distribution. So it should look like something more or less like this. So it's like a bell curve. Of course, this is a discrete distribution, but still it can be approximated as a normal distribution. Okay. Just to refresh your memory, the average, the mean of Poisson distribution is what? So if you have the Poisson distribution with parameter lambda t, then okay, so this nt follows Poisson distribution. So the expectation value of nt is lambda t. And also the variance of this, do you remember? It's a Poisson distribution, so the variance, so you can just examine this by directly calculating the variance according to the definition. It should be also lambda t. It's a Poisson distribution. So this approximate normal distribution should have the mean that is lambda t, and the variance or standard or variance should be lambda t also. So the standard deviation should be square root of lambda t. Okay. Now we explore some implications of the Poisson process. So as we have discussed before, its probability is defined by the Poisson distribution with parameter lambda t. So when n is equal to 0, then we have this. So if you differentiate both this function with respect to t, we have this. You know, t is a continuous variable, so it is okay to differentiate with respect to it. And the result is negative lambda exponential of negative lambda t. Okay, so in other words, this is the differential equation that must be satisfied by the probability distribution of this Poisson process with n equal to 1. Okay. Then, if n is not equal to 1, so that is n is greater than 0, and not equal to 0, so n is greater than 0, then if we differentiate this Pn of t with respect to t, we have, so we use the product rule. I think that's what it's called. So we differentiate with respect to t, this part first, then this part next. So the first part, we have n lambda t, n to the power of n minus 1, and by the chain rule, it's lambda stays here. And this one is still this. And the next term, lambda t to the power of n doesn't change, and this part is differentiated, so that's negative lambda and exponential of lambda t. Okay, so let's see, we have let's see, this part, this part, this part, this part, and this part common. So if you factorize, we should have, let's see, wait a minute. Let's see. So this n and one n here is cancelled. So they are cancelled. So that means we have lambda t to the power of n minus 1, lambda t and n minus 1 factorial. And we have negative lambda, and lambda t to the power of n e lambda t and factorial. Now, this part is actually Pn minus 1 of t, and this part is Pn t. So we have this lambda times Pn minus 1 of t minus lambda Pn of t. So, okay, let's move this again. Pn of t dt. So this is the differential equation or differential difference equation, because this involves derivative as well as difference between these two terms. So it's differential or differential equation, differential difference equations. Okay, so we have this for n equal to 0 and this for n greater than 0. So this set of differential difference equations can be considered as the defining equations for the Poisson distribution. Because if you solve this differential difference equation, what you get is this as the solution, right? This is the solution of these differential difference equations. So we can define the Poisson process by this probability distribution, or by this set of differential difference equations. Either is okay, and they are equivalent. Oh, I think I forgot to mention that this differential equation for P0 can be expressed as lambda, negative lambda times P0 of t. Right, so this is the differential equation for P0. Okay, so after all, we have this. So we have this differential difference equation, differential difference equations, and that it's satisfied by this function. So this is the solution. This is the solution of these differential difference equations. Okay, so if you are familiar with differential equations, then this system of differential difference equation seem very easy to understand. But if you're not, it may be easier if you translate this in terms of difference equations. So if we go back to the definition of derivatives, we have this. So dpn of over dt is this: limit delta t going to 0 and pn t plus delta t minus pn of t divided by delta t. So if this delta t is close to 0 in the limit of 0, then that becomes this ratio becomes the derivative. Okay, so this means we can approximate this derivative by this term. Okay, and we assume this delta t is a small value. Okay, so if we substitute this definition into the left-hand side of these differential difference equations, we have this. First one. First, let's try this one. So the left-hand side becomes this over delta t. That is equal to lambda p0 of t. Actually, this is approximation. So we have some extra factor. So that is O delta t. So this means some higher order terms of delta t, and that is higher order than delta t itself. Okay, So what this means is that so there is something here, extra terms, but that will converge to 0 as delta t goes to 0. Okay, so therefore we can ignore this in the end. Okay, so if we multiply both sides by delta t and move this term to the right hand side, we have p0 t plus delta t equal lambda p0 t times delta t plus p0 of t. So, and we ignore this term, okay? It will disappear anyway as we move delta t to 0. So, factorize this, then we have 1 minus lambda delta t times p0 of t. Okay, and do the same thing for the second equation, and you should have something like this: pn t plus delta t equals to lambda delta t times pn minus 1 t and 1 minus delta t 1 minus lambda delta t and pn of t. And again, we should have this all delta t term here, but we just ignore it. Okay, so now we have this difference equations. Okay, so now what do these mean? Okay, first of all, what's the meaning of this lambda delta t? Lambda delta t. We have lambda delta t here, 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 here. Okay, and notice that if we add lambda delta t with 1 minus lambda delta t, this result in 1. Okay, so this looks like probability. Lambda delta t looks like a probability of something. In fact, we can interpret the meaning of lambda times delta t like this. So lambda delta t is the probability that the number of this integer is equal to n plus 1, given that n at t is equal to n. Okay, so in this Poisson process, this integer value, this random variable n of t, can only stay the same or increase. It can never decrease. Okay, so this parameter lambda is the rate of increase of this number. Okay, during the duration of delta t, this time duration of delta t. Okay, so this probability, given that this number is n. Okay, so let's see. So if we plot n of t, so at time t, this was n. Okay, and after delta t, let's say delta t, so this is t plus delta t. Okay, so after delta t, this may increase to n plus 1. Okay, and this probability is given by lambda times delta t. So this is proportional to the duration. So this, if this delta t increases, then the probability also increases. But this is, of course, an approximation, because this linearity cannot hold indefinitely, because if delta t is very large, then lambda t will become eventually greater than 1, which violates the axiom of probability measure. So this interpretation is valid only for small values of delta t. Okay, but it's okay, because in the end we take the limit of delta t going to 0, so delta t should be small. So what is the probability that this random variable n does not change after delta t? As I have said before, there are only two possibilities. Either this number increases or stays the same. And if this delta t is small enough, this number cannot increase more than 1. Okay, so this cannot, during delta t, it cannot go like this, like n plus 2 or n plus 3 or etc. So these probabilities are very rare, so we can ignore it. So if it increases, it can only increase by 1. Okay, so otherwise it stays the same. So that probability will be equal to 1 minus lambda delta t. Okay, so this cannot happen. Only this, so one step higher, or it stays the same. Okay, if you consider this, then the meaning of the first equation should look obvious. So the probability that the number of this random variable n of t is 0 at t plus delta t is equal to the probability that it was that n was 0 at time t and it stays the same during the duration of delta t. So that is this. Okay, so it means this. So the number was 0 when time was t, and when t plus delta t, then it stays the same. Okay, but this transition probability is 1 minus lambda delta t. Okay, so the probability that the state was 0 is given by p0 of t, right? So this probability was this. And the probability that this n is 0 at time t plus delta t is given by p0 t of delta t. And the transition probability is 1 minus delta t, 1 minus lambda delta t. So therefore, we have this difference equation. So 1 minus lambda delta t and this. So maybe it's easier to understand if we write this more explicitly. So this is 0 given that n of t was 0 times the probability of n being 0 at time t. Okay. So next difference equation, this one, consists of two terms, this and this. Now, how can we calculate the probability that the random variable n of t takes the value of n at time t plus delta t? So let's see. So this is t, and so at time t, it has some value, and at time t plus delta t, it has the value of n. Okay, so this point, wait a minute, this point can be reached via two ways. First, at time t, it was already n, and it stays the same during the duration of delta t. And this transition probability is 1 minus lambda delta t. And the other choice is the number was n minus 1 at time t. Then it increased by 1 during delta t. So this transition probability is lambda times delta t. Okay, so this probability that the number is n at time t plus delta t is either coming from this path, lambda delta t, when the number was n minus 1 at time t, or it comes from this path, so 1 minus lambda delta t, so it stays the same, and it was already n at time t. Okay, so if you prefer, we could write this part as probability of n t plus delta t is equal to n, given that n of t was n minus 1. So this is equal to lambda delta t, and Pn minus 1 of t plus probability that n of t plus delta t is n, given that n of t was already n, and Pn of t. So this is the second difference equation here. So what's the use of the Poisson process? As you may know, the Poisson distribution is often used for modeling something that is rare to happen, right? So for example, the number of accidents. So let this n of t represent the number of accidents that have happened until time t. Okay, so if we plot the number of accidents along time, so let's start measuring the number of accidents from here. Then there will be no accidents for a while, but one accident happens, and then after some time another accident happens. Maybe we are unlucky and some accidents happens uh, very often during some period. Then it may stay at the same value for a while, and then another accident happens. Okay, so something like that. Oh, maybe this is not good. So the number of accidents, and another example may be nuclear decay of some radioactive substances, so which can be counted by a Geiger counter, and yeah, those kind of stuff. Something that are rare. Accidents is a very popular example, and plane crash, of course, that's another kind of accidents, and nuclear decay, and so on. Okay, now we reverse the argument. So forget about Poisson processes. Okay, so assume, just pretend we don't know anything about the Poisson process, and but we want to model something uh, that that changes over time. Something is a count of something. Okay, number of something like a number of Geiger counting by Geiger counters, or number of accidents. So those numbers have integer values, non-negative integer values, 0, 1, 2, 3, and so on. And it varies over time and only increases or stays the same. Okay, something like this. So now, uh, so assume the probability that one accident happens during short time interval delta t. Okay, so let's say this probability is a function of delta t. Okay, duration of time. So consider this as, so expand this in a Taylor series. Then we have something like q of 0 plus q prime of 0 times delta t plus uh, q double prime 2 factorial and delta t squared and so on. Okay, now since this q of delta t represents the probability that one accident happens during delta t. So when delta t is 0, everything here is 0. So this q0 remains. But this should be 0. Otherwise, something can happen with no time, within 0 time duration, right? So that's not reasonable. So we should have this 0th order term as 0. So we just erase that. Now this q prime of 0 is just a constant, so let's call it lambda. Okay, so we have lambda delta t, and everything else, higher order terms, are summarized as O delta t. Okay, so because this has delta t squared and the next term is delta t cubed, so they are all higher order terms. So if we take this ratio, O delta t over delta t, this converges to 0 as delta t goes to 0, right? You should calculate. So you should divide all these terms by delta t, and if we move delta t to 0, everything here converges to 0. So eventually we can ignore this term. Okay, so as the same argument as before, but going backwards, the probability that the number of accident is 0 at time t plus delta t is given by this probability. So no accident happens during delta t. So that probability should be this. This all delta t can be negative or positive, but it doesn't matter. So we just write positive. So this just says something of higher order of delta t. Then this times uh, probability that the number of accident was 0 at time t. And similarly, for n greater than or equal to 1, we have Pn t plus delta t. So either the number of accidents were n minus 1, in which case one accident happens during delta t. So the number of accidents was n minus 1 at time t, or no accidents happens during delta t, but the number of accidents were already n at time t. So these two equations should hold. You know, remember, we are not assuming Poisson process here. We are just simply assuming the probability of one accident happening is given by, can be approximated by this linear equation of delta t. Okay, that's all we are assuming. So as we have seen before, if you arrange these equations, we have something like this: p0 t plus delta t. You should derive this yourself. Over delta t is equal to negative lambda p o t, and actually we have extra term here, o delta t over delta t and p0. But this term will eventually disappear as delta t goes to 0. And Pn is the lambda plus O delta t, lambda t, and Pn minus 1 of t minus Pn of t. Okay, so now let t go to 0. Then on the left hand side we have the derivative of p0 and pn, and on the right hand side these terms involving small o's will disappear. So after all, we have these differential difference equations. dp0 is ugly. p0 dt minus lambda p0t, and dpn t dt lambda pn minus 1 of t minus lambda pn of t. So now we have these differential difference equations and we want to solve them. Okay, to solve them we need initial conditions. Okay, and what's the initial condition in this case? That is, at time t there were no accidents. Time t equal to 0, there were no accidents in the beginning, right? So that should be 0. So time t, at time 0 there is no accident, so this is this probability should be 1. Okay, so everything else should be 0 when n is greater than or equal to 1. So these are the initial conditions for solving these differential difference equation. Alright, so we want to solve these equations, and I will show two ways to solve these differential difference equations. So the first one is called the iterative method. So iterative. So that is just start solving these differential difference equations starting from n equal to 0. So the first one is easy. So p0 dt negative lambda p0 of t. So this is easy to solve, and if you are a math measure, then once you look at this, you should immediately be able to solve this equation. So this should be something like this and some constant times exponential negative lambda t. And this c is a constant to be determined from the initial condition. So what was the initial condition? So p0 of 0 is equal to 1, right? So this, if you substitute t equal to 0, then this term is 1 and that is equal to 1. So the value of c is 1. Therefore, we have this. So that's the solution for p when n is equal to 0. Now, consider the case where n is equal to 1. So we substitute n equal to 1 in this equation. Okay? So if we do this, we have dp1, just omit of t. Okay, so that is lambda p0 minus lambda p1. Okay, so move this to the left hand side. We have plus lambda p1 equal to lambda p0, which we already know what that is. Okay, so that's lambda e to the power of minus lambda t. Okay, so let's look at this. Now, okay, let's multiply both sides by the inverse of this. So, in other words, we want to get rid of this term, this exponential term from the right-hand side. So that becomes, let's see, e lambda t dp1 dt plus lambda e lambda t p1 equal to lambda t. Okay, and now look at the left hand side. So this is, if you look at this times this and this times this, and this lambda e exponential lambda t is actually this. It's a derivative of exponential of lambda t, right? So that means we can write like this: lambda t, okay, p1 derivative, and e lambda t derivative p1. So that is derivative of lambda e to the power of lambda t times p1, right? So after all, we have, so now we can integrate both sides with respect to t. Okay, so maybe we should write like this. Okay, integrate both sides with respect to t, and we get exponential lambda t p1 of t equal to lambda t plus constant. Okay, so this constant is determined from the initial condition. What was the initial condition for p1 of 0? That was 0, right? At time 0, there were no accidents. Okay, so the probability of there being one accident at time t equal to 0 is 0. So from this, if you substitute this initial condition, this becomes 0, and this is 0, and this is 1, so c should be 0. Okay, so we have this. So therefore, by dividing both sides by this factor, we have P1 of t is equal to lambda t times exponential negative lambda t. So that's the solution for P1. Okay. Now what about P2 next? Oh, let's see. So if we apply the same technique, we have this differential equation. P2 dt plus lambda P2. Let's see, just this, and that is lambda P1. But if we substitute the result of P1, we have lambda squared t times exponential of negative lambda t. So now we apply the same technique. So multiply both sides by the inverse of this. Then after all, we get something like d dt and exponential lambda t p2 equal to lambda squared t. So if you integrate, we have lambda e lambda t p2 lambda lambda squared t squared over 2 plus constant, and the initial condition is p2 of 0 is 0, so this c should be 0. Okay, then from this we obtain p2 is equal to lambda t squared over 2 times exponential of lambda negative lambda t. Okay, now you use this result to solve the equation for p3, then p4, then and so on. So after all, you will find that the general solution for Pn is given by this: lambda t to the power of n divided by n factorial times exponential of negative lambda t. Alas, this is the Poisson distribution with parameter lambda t. So in this way, we discovered the Poisson process, starting from the very simple assumption that the probability of one accident happening during small amount of time, delta t, is linear, linear to delta t. So now we understand what the basic assumption for the Poisson process is. That is, so that is this. So the probability of one accident happening during delta t is just a linear function of delta t. So that is the most basic assumption for the Poisson process. Now next, we solve the same problem by using the method of generating function. Okay, for your information, this is the generating function in this case. We are dealing with the probability generating function. Okay, and t is time and s is a dummy variable used for generating function. Okay, so in this case, it's defined like this: from n equal to 0 to infinity, and this is the probability function we want to find, and s is the dummy variable, and s to the power of n. So this is the definition of the probability generating function, PGF, probability generating function. Okay, Using this, we want to solve that those differential difference equation. Okay, so let's see. For n equal to 0, we have p 0t dt equal to negative lambda p0 lambda t. Okay, again, remember, we are pretending that we know nothing about the Poisson process. Okay, all we know is this system of differential difference equations. Okay, then for n equal to 1, we have dt and lambda p0t minus lambda p1 of t. And for n equal to 2, p1 of t minus lambda p2 of t, and so on. So in general, we have pn lambda pn minus 1 t minus lambda pn of t. So we have these equations. So this continues forever, okay, to infinity. Now, let's multiply both sides of each of these equations by the power of s. Okay, in this case, we multiply both sides by s to the power of 0, which is just 1. And in the second case, s to the power of 1, which is just s. And the second, when n is equal to 2, power to the power s to the power of 2. And in general, s to the power of n. Okay, we should have s here also. S and s squared and sn. Okay, so we multiply both sides by the same power of s. Okay, s to the power of n, s to the power of n, s to the power of n. Okay, then add all these terms. Okay, so add this plus this plus this plus this plus and so on, and add everything. So we have negative lambda here, negative lambda here. So add all these terms, and we have positive lambda here, here, and so on. So we add all these terms together. Okay, so if we add them, so let's add them all, and the left hand side becomes sum n from 0 to infinity dpn of t dt s to the power of n. And the right hand side is made of two summations. First, the sum for all of these with positive lambdas. Okay, so they will be, so I factor out lambda out, so lambda summation, so n starts from 0, and from 0 to, wait a minute, yes, and from 0, but remember, this n is 0 here, but the power of s is 1 here. This is 1 here, the power of s is 2 here. So the power of s is uh, one more than this index of p. Okay, so this becomes p, let's see, pn of t and sn plus 1. And the other summation is over these terms. Okay, so those are negative lambda and sum over n starting from 0. Okay, so that's fine. And pn of t, and this n and this n are the same n. So pn of t times s to the power of n. Okay. Now, let's see what we can do. Let's see. First, we have extra s here. Extra s. So let's put one s out. Okay, so one s out. So this becomes lambda times s, and n from 0 to infinity Pn of t times s to the power of n. Okay, and this one is fine, so just as it is. But now look at this. This one and this one are the same thing. Okay, and this is actually the probability generating function, right? This one. So it's summation from n equal to 0 to infinity Pn of t times s to the power of n. So that's exactly what these are. So what we have here is, so this one becomes the generating function s of s g of st. This one is the generating function s of st. So if we combine these together, we have lambda s minus 1 g of s of s and t. So generating function multiplied by lambda and s minus 1. And what about the left hand side? If you look at this, s is just s, it has nothing to do with time t. So we can just move this differentiation operation outside of the summation. Okay, so that means, okay, in this case we have actually partial differentiation with respect to t of this summation Pn of t and s to the power of n, because now we have two variables t and s. So we are just differentiating with respect to t alone. So if we move this differentiation outside the summation, then it should be the partial differentiation rather than the total differentiation. Okay, so after all, after this, if you look at inside this differentiation, what is this? This is actually the generating function, right? So after all, we came up with this partial differential equation of the probability generating function. Okay, so now how can we solve this partial differential equation? So this is partial differential equation. Oh, PDE. Okay, but fortunately we have only one derivative here with respect to time only. There is no derivative with respect to s. So actually this is easy to solve. So we can solve this equation just like an ordinary differential equation with respect to time. Okay, so if you solve this, this is easy. So this is just function of t, function of t. So and these coefficients do not involve t, so they may be considered as constant. I mean, as far as t is concerned. So if you solve this equation, this is a very basic differential equation. So you should immediately come up with this solution. So some constant and exponential with of lambda s minus 1 t. But actually this constant may depend on s. Okay, this is a constant with respect to t, but it may contain s. So in general, this is a function of s. Okay, so some function of s times exponential of this lambda s minus 1 times t. Okay, now we want to determine this function as a of s. So how can we do that? Now remember that the initial condition, it was p0 of 0 is 1 and pn of 0 is 0 if n is greater than or equal to 1. Okay, we use this fact. Okay, so if we substitute t equal to 0 in the generating function as 0, then this is by definition Pn of 0, this. Okay, so this should be equal to 1. Because if n is 0, then the power of s is 0, so that's 1. And p0 of 0 is 1. And everything else should be 0. So the only term left is 1. So this is 1. So now, if you compare this value with this value with t equal to 0, when t is equal to 0, this term, so this is 0, so exponential of 0 is 1, so that is a of s should be equal to 1. So it's actually a constant. It doesn't involve any function of s. So after all, so if you substitute this result, we have g of st is equal to exponential of lambda s minus 1 times t. So that's it. That's the generating function. Okay. Now, then what's so nice about this generating function? What's nice about this generating function is that if we expand this in terms of s, in powers of s, then we get the probability functions, distributions. Okay, let's do it. So first, we get rid of this negative one. So that's lambda s minus lambda t, which is lambda s times e minus lambda t. So this one is fine by itself, and we expand this exponential term. So that becomes, this is just an expansion of exponential function. Okay, wait a minute. This should involve t here. So s times t, right? So this is just exponential function. So just apply the Taylor series of exponential function. That is lambda st to the power of n over n factorial, and times, of course, this term. But what is this? So let's arrange this in this form. So this is just power. So lambda t to the power of n exponential of minus lambda t, so this one, and over n factorial times s to the power of n. Okay, now compare this with the original definition of this generating function. that was Pn of t times s to the power of n. So this s to the power of n is this s to the power of n. So this part and this part should match. Therefore, we have Pn of t equal to lambda t to the power of n exponential negative lambda t and n factorial. So this is the result, which is nothing but the Poisson distribution. Now you should review how we got this result, okay? Because we are going to use this technique of generating function repeatedly for other problems. Now let us look at the Poisson process from a different perspective, and it's called the problem of arrival times. So let's see. Let's consider this problem of phone calls. So suppose we count the number of phone calls by time t. So for some time we have no phone calls. Then at some point we get one phone call. Okay, then we wait a little bit more. Then at some point we get another phone call, and so on. Okay, maybe we can get many phone calls consecutively, like this. So let's see. So this time where when we get the first phone call, let's call it T1, and the time of second phone call, let's call it T2, and so on. So we have Tn, and also let's see, this is Tn minus 1, and also we define the time between two consecutive phone calls. So this time between T1 and T2, let's call it Q2, and the time between Tn minus 1 and Tn, let's call it Qn. So Qn is Tn minus Tn minus 1. Okay. So we want to find the distribution of this time. Okay, this interval. What is the probability distribution of this interval? So arrival times, inter-arrival times. Okay, so first of all, the probability of having no call at time t is given by this. So this, since we are modeling this as a Poisson process, okay, so this number follows the Poisson process. So the probability of no phone calls means probability of zero phone call by time t. So that is given by this exponential of negative lambda t. Okay. Now, next, we want to calculate the probability that the first phone call happens by time t. Okay, so this means the first call by time t. So we want to calculate this probability. So this means we have at least one phone call by time t, right? So that is P1. Maybe we get one phone call by time t. And maybe two phone calls by time t. Or three phone calls. Or etc. So whatever, however many phone calls we get, it should be greater than 0. Okay, so that's what this condition means. So T1 is less than or equal to small t. Okay, so t is somewhere here. So as long as this t1 is less than or equal to this given specified time, then that's our event. Okay, but this is equal to all the possibilities, any number of phone calls except for 0. So this should be equal to 1 minus p0 of t. Okay, so which is 1 minus exponential of minus lambda t. Okay, now what we are interested in is this time interval between two phone calls. However, you should note that this event, so Qn is less than small t, this event should be equal to this event. T1 is less than or t. Why? Because each phone call is independent from other phone calls. Okay, so after n minus 1 phone calls have been received, then the time until the next phone call is independent of all the previous phone calls, right? So every nth phone call is the first phone call since the last phone call. Okay, well, every phone call is the first phone call since the last phone call. So that should be the same as this event. Therefore, this. Okay, so this means their probabilities should be the same. So Qn less than or equal to t is equal to t1 less than or equal to t, which is 1 minus exponential of negative lambda t. But now, what is this probability? This is actually the distribution function of Qn, right? So this is another name for distribution function is the cumulative distribution function. Okay, so this is actually the definition of the cumulative distribution function. Well, in statistics, we tend to use this term, but in probability theory, we just say distribution function. We usually omit cumulative. But anyway, so since this is the cumulative distribution function, we can find the probability density function of t by differentiating this cumulative distribution function with respect to t. So the density function of t is given by the derivative of f of t. So since cumulative distribution function is this, the result is lambda exponential minus lambda t. So what is this function? So this is the density function for density of Qn, right? So by the way, Qn is of course the continuous random variable. Okay, so it has the density function, and the density function is this. And I think this should look familiar. This is actually an exponential distribution. With parameter lambda. Okay, so we write something like exponential distribution with parameter lambda. Okay, so as such, we we can calculate its mean value and variance. So the mean of Qn, since this is just exponential function, you can just, of course, t varies from 0 to infinity. So t is greater than 0 and less than infinity. Okay. So yeah, you can just calculate this using the standard technique and definition. And this should be 1 over lambda. And variance of Qn is 1 over lambda squared. Okay. Now, by the way, this lambda should have some unit, right? And in the beginning, we modeled the probability of transition from n minus 1 to n during time duration of delta t as lambda delta t. So this should represent a probability, right? And the value of probability should not have any unit, any physical unit like meters or kilograms or seconds or whatever. So this is just a number. However, delta t is supposed to mean time. So this has a unit of time. Okay? So that means lambda should have a unit of inverse of time. Okay? So lambda should have a unit of inverse of time. So let's say inverse second, something like that. Right? So if you take the inverse of lambda, then 1 over lambda should have the unit of second, time. So it makes sense because Qn represents the time, duration of time between two phone calls. So this should represent, uh, uh, this should have the unit of time. And 1 over lambda does have the unit of time. So it is consistent. And same for the variance, right? Variance is time. It should be of the unit of time squared. So so 1 over lambda squared has the unit of time squared. Okay. And next, let's consider the distribution of Tn. So what's Tn? So Tn is the time at which the nth call arrives. Okay, so what is the distribution function for Tn rather than Qn? So Qn is this, each interval between two consecutive phone calls. Okay, but Tn accounts all the phone calls up to this point, n phone calls. So what's the distribution of that? So to calculate the distribution of Tn, consider this. So we want to calculate the distribution function of this Tn. So maybe we should write Tn here. So that is the probability that Tn is less than or equal to some given time t. So what does it mean? Okay, so this means n or more phone calls have arrived by time t, right? So this Tn is less than some given constant time t. So that means if you put any value t here, so this Tn should be less than or equal to that value. So that means at least n phone calls have occurred by time t. So it could be that maybe n plus 1 or n plus 2 or n plus 3 phone calls have arrived already, but it doesn't matter as long as Tn is less than or equal to this given time lowercase t. So we don't care how many more phone calls have arrived. So anyway, so this should be probability Pn of t. So that's exactly n phone calls by time t, or exactly n plus 1 phone calls by time t, or exactly n plus 2 phone calls by time t, and so on. So that is so it's summation of r from n to infinity and pr of t. So from the distribution function for the Poisson distribution, we have lambda t to the power of r and r factorial exponential of minus lambda t. So the density function for Tn, so let's call it small t, f Tn of t, is given by the derivative of this. Okay, so this is a little bit involved, but you should check that this should be equal to this lambda t to the power of n minus 1 exponential lambda t over n minus 1 factorial. So the derivative of this distribution function can be simplified to this form. So that's the density function for Tn. Okay, density of Tn. But what is this exactly? Well, maybe you don't notice, but this is the density function for the gamma distribution. With parameters n and lambda. Okay. Does it make sense? So the distribution, the distribution of Qn, so each interval was an exponential distribution. And the distribution for Tn, that is the time until n phone calls, is the gamma distribution. Does that make sense? How are they related? Okay, now consider this. So if you consider the relationship between Tn and Qn, so let's say that's T1 and that's T2, T3, T1, T2, and T3, T4, and let's say this is Tn minus 1 and Tn. Okay, so this should be Q1, this should be Q2, and Q3, and so on up to Qn. So Tn should be Q1 plus Q2 plus up to Qn, right? And each of these, Q1, Q2, Qn, they all follow the same exponential distribution. Okay, so Qi, where I varies from 1, 2, 3, up to n, all follow the same exponential distribution with parameter lambda. Here. So Tn is the sum of all these exponential random variables. So identically distributed. And also these are all independent. You know, Q1, Q2, Q3 up to Qn, they are all independent. So that means they are all independent, identically distributed, IID. Okay, so T is the sum of IID exponentially distributed random variables. And if you remember the result from intermediate statistics, that follows gamma distribution. Gamma distribution with, so if there are n terms in the summation, the gamma distribution with n and lambda. So lambda this is this lambda of exponential distribution. So gamma distribution with parameters n and lambda. So that's what it is. And in fact, if you calculate the mean of this Tn of gamma distribution, then it is n over lambda, which is n times the expectation of Qn, right? And also the variance becomes n over lambda squared, which is n times the variance of Qn here. Qn. That's because these random variables Q1 to Qn, they are all independent, identically distributed exponential distributions. Okay, that's all for the Poisson process.